Hello everybody, welcome to Embedded ARM Dev. In this video we're going to explore the ELF program header table and discuss segments. If you haven't already done so, I recommend you check out my other videos that introduce the Linux ELF file header and section headers, which will be helpful for understanding the material in this video. The goal of this video is to describe the structure of the ELF program headers, which describe segments. You might sometimes hear the term segment header instead of program header. These are just two different terms for the same thing. In this video, I'll be using the term program header since it's more standard. So first we'll look at the elf.h file to examine the structures and definitions that describe the program header. Then we'll cross-compile a simple program so that we can examine its program headers. We'll use the tool readelf on the binary to get a readable output of the program headers. We'll also examine the program header for an example segment in the compiled binary, which will be in hex code. And we'll use all this information to examine each field of the program header structure. Okay, so here we are on my Ubuntu system. Right here, this hello.c, that's just a very typical hello world program. And we're going to cross-compile this using the ARM compiler, and then we're going to examine the binary using readelf, and we'll go through and look at the program headers in one specific segment. So to compile this, I'm using a pre-installed cross-compiler. So remember, this is a cross-compiler, not a native compiler. And the resulting binary will be for the ARM architecture. So I'm going to call this hello ARM, just so it's clear that this is an ARM file. Okay, and then we do a list and we can see that we've got this hello ARM here now. And if I run file on it, it tells us that is ARM and it's a LSB executable and it's dynamically linked. That's because we have this printf in here. The next thing we're going to do is we're going to call readelf on this binary so that we can get some generic information about it. So the -h gives us the file header information, and I covered this in another video, so if this isn't familiar to you, go ahead and check out my video on Linux ELF file headers. So we'll use this information, but the kind of thing we're looking at right here is where the start of the program headers are, and then these two values right here, which is the size of the program headers and the number of program headers. So that's information we'll use. And the next thing we're going to do is we're going to do readelf.l, which gives us the information about the segments. We see here that there are 9 program headers starting at offset 52, and these are the segments. This information so each one of these is a segment, and a program header describes one of these segments. So each row here, all this information is contained in the program header. Each one of these is a field in the program header, and we'll go over each of these. And the next thing worth looking at is that this output gives us this section to segment mapping. So generally the segments will span multiple sections. As far as the linker loader is concerned, it doesn't care about these sections. It doesn't need this information. In fact, sections don't even need to exist for the program to be loaded into memory. But it's useful for debugging and possibly reverse engineering and other efforts to understand where, how the sections and the segments map together. So this is information that can be helpful to you. The next thing I want to look at is the actual ELF file. So this ELF file is, this elf.h is what is going to define all of these structures and that kind of stuff that we're going to be looking at. So let me just find so I finally found it. So this is the segment header or program header. Sometimes you'll hear them called program segment header. These structs here are defining the program header entry, so one record inside the program header table. So you can see here there's a 32-bit struct, and then you have a 64-bit struct. So it just depends on which system you're compiling for. And we will examine each field in these. Now for this video, I'm only doing 32-bit, but you can see that they're basically the same. And then as you get further down in here, you'll see these legal values for the different fields. For example, we got p-type here is one of the fields, and then this lists all of the legal values for that field. P-flags, so all the information that you need to decode the program header. One program header is down here in the following. So we'll examine each one of these throughout the video. but I just wanted to show you where you can find these definitions. Okay, so for this video, I'm going to use the Bless hex editor here. You can install this using apt or apt-get. So basically, you just take your binary and drag it in there, and it gives you the hex display of the binary file itself. So this is what I'll be using as we examine the hex output for the file. So first, let's answer the question, what are program headers and what are segments? So a program header is a structure that describes a segment. And a segment provides information that relates to the program during execution. So as it appears in memory versus as it appears on the file. So the segments describe information needed by the linker or loader to load the binary into memory and execute the program. So this quote that I have here from the man page for ELF is an executable or shared object file's program header table is an array of structures, each describing a segment or other information the system needs to prepare the program for execution. Okay, so here we have the struct that defines a program header, which describes a segment, and this is for the 32-bit system. So just note that these words, offset, and address values are just type defs. I pulled this out of the elf.h file. So you can see here that every field in this particular struct is a 32-bit field. So all of these fields right here are each 32 bits. So we'll go through each of these fields in detail throughout this video. Alright, so here we have the structure for the program header on a 64-bit system. One thing to note is that in this struct, the P flags is the second field, whereas on the 32-bit structure, it was down here between mem size and a line. Another thing to note is that we've got these type defs over here, which I pulled out of elf.h, and the elf64 word value, note that it is a 32-bit. So these first two fields right here are going to be 32 bits. Also note that in general, any reference to an address, an offset, file size, memory size will align with the system is compiled for. So all of these right here will be 64 bits, and on a 32-bit system, they would be 32 bits. In this video, we'll be using a 32-bit structure because the program that I compiled it for a 32-bit architecture. Okay, so the first thing we're going to do is examine the output of the file header and see what information we get about program headers and segments. So the first thing we note is that this tells us here that the start of the program headers is 52 bytes into the file, and 52 is equal to hex 34. So one thing to note is that this is where the program header table starts. It is not where the segments themselves reside. The second thing we want to look at is the size of the program headers. Now this value here is the size of each header. Okay, so each entry in the header table is 32 bytes. And then this also tells us the number of program headers. So there are 9 total program headers in this. Okay, and so if we do the math, we take 32 bytes times 9 headers, and we get 288 bytes, which is hex 120. So that means the program header table itself is 288 bytes in the file. Okay, so here we have the output from readelf showing some of the program headers. So you can see here there are a total of 9 headers and numbered 0 through 8. Note that these numbers right here, I added these for our reference, and you will not see them in your output or your readelf output. So each one of these entries describes one segment, and each column here is a field inside the struct that we looked at. So one thing that's interesting here is we see that index 1, the P header or program header, this is the actual program header that defines all of these segments right here. So this is the location where this data is. So here we can see that the program header segment is located at hex 34 bytes, which is 52 bytes in decimal. And also we can see that the file size, the size on the file is 120 bytes in hex, which equals 288 bytes. And if you remember, that is what we calculated previously examining the file header information. Okay, so here we have the second part of the output that we get when we use the readelf.l option, which gives us the program header information. And so this is a mapping of segments to sections. So the data in a segment can span many sections. So we see here that segment ID number 3 spans all of these sections right here, and segment ID number 4 spans these sections here. So over here we've got this little layout that kind of shows how things are laid out in memory for a typical ELF file. So first we have the file header, which is generally the first thing in the file, followed by the program headers, which is what we're discussing in this video. Note that the section headers, which we discussed in a previous video, are generally the very last thing inside this file. And then in the middle we have all the sections, and then these segments kind of map to these, or they span these sections. And so this mapping tells us basically, how these sections align with the segments. So remember, from a file perspective, each section contains different data for different uses. However, from the program execution perspective, the segment is just one big chunk of data, and the loader doesn't need to have any understanding of the layout of the sections. However, it can be useful to debugging and reverse engineering efforts to understand how the sections and segments align. Okay, so next we're going to go through and describe each field in a program header. To do this, we'll use this number 4 program header right here as an example. From a program execution context, these load segments are arguably the most important because this actually gets loaded into process memory. Okay, so what we're doing here is calculating the file offset for the program header for segment 4, which is the segment that we're using as an example. So we know from the file header that the start of the program headers is 52 bytes into the file, which is hex 34. And then we know that the size of one program header is 32 bytes each, which is hex 20. And the index of the load section that we're interested in is index 4. So what we do here is we take this value, so it's 32 bytes per index times 4, gives us an offset of 128 bytes into the program header table. And since we know the table starts at 52 bytes in, or hex 34, if we add these two together, so this is the program header table offset where it starts, and this is the offset into the program header table. And so we know that in the file offset, we were looking at hex Bravo 4, B4, for program header number 4. If you look here, I got this little diagram here that shows, the file header is at offset. Now this is the offset in the file. So offset 0. So the program header 0 for index 0 would be at 34. And then each one of these is 20 bytes in hex. So it's 34, 54, 74, and it increases like that. So the program header that we're looking at is at Bravo 4. I've got the hex code from the Bless editor, and we're looking at right here, this is Bravo 0, so Bravo 0, 1, 2, 3. So it starts at Bravo 4, and it goes all the way down to here. Okay, so if you do the math, you'll see that is 32 bytes. Okay, so the first field we're going to look at is the p-type, and the p-type just indicates what type of segment it is. And so here we've got the struct. You can see it's the first field, which is a byte offset of 0 bytes into this struct. Okay, and since we have our offset for our header is B4 into the file, and the offset for this is 0, so we have these 32-bit value right here, which it indicates our segment type. Now note, this is Little Endian, and so it reads backwards. So the actual value is 00000001. Okay, so a p-type of 0x01 corresponds to pt load. Okay, so down here we have, I pulled this out of elf.h, and these are the most common p-types that you'll see. Load, so load right here, this type right here, 1, is a loadable program segment. So this is something that will actually get loaded into process memory. And again, we talked about the program header here, so that would be the program header table entry. And then there's some other ones that are used like dynamic, the interpreter, which I will go over later in this video, and some of these other ones. Okay, so the next field we're going to look at is the p offset, which you can see here is the second field. And this offset indicates the file offset where this segment starts. So this is the offset inside the file, the binary file, where this particular segment we're looking at starts. And so if you see right here, an offset of 4 into this program header, we have a value, a 32-bit value of 00000 Fox 0 Charlie. So we bring that here, and that tells us where in the file this particular segment starts. So if we look at the hex editor here, we can see that at 0 Charlie, this right here is the start of that segment, the actual segment data itself. So that tells us where it is in the file. Okay, so the next field we're going to look at is VAddr, which is the third field here. And this is the segment virtual address. So this indicates the location in memory where the segment is expected to be loaded. This may not always be true in reality because some operating systems will use something called address space layout randomization, or ASLR, which may not necessarily be the actual load address in memory. And so ASLR is a way to prevent binaries from being exploited, being attacked. And basically what it means is every single time the binary runs, it gets loaded into a different address. And this makes it difficult for attackers makes it more difficult because they can't hard code addresses. So we see here that this is the field right here, and it's 020 Fox 0 Charlie. So you come down here, we got 020 Fox 0 Charlie. And so that is the address that the binary expects to be loaded into when it gets loaded. All right, the next field we'll look at is the P address, or the physical address. So in some systems for which field addressing is relevant, this member is reserved for the segment's physical address. This member requires operating system specific information. Many times this is going to be the same as the virtual address, and you can see here that that case is true for this particular binary. So it depends on the system you're compiling for, and if it uses virtual memory, this could be different. It just depends on the system you're compiling for. All right, so the next field we'll look at is the file size, which is this one right here, segment size in file. So what this is telling us is how much space this segment takes up in the file. It's possible it can be 0. It doesn't have to be, it could be completely, like it takes up no memory in the file. And so we see here that we have 0000011 Charlie. Okay, so that value right here is the P file size, and that comes out to 284 bytes. So this particular segment that we're looking at has a total size of 284 bytes. So the next field we're going to talk about is the mem size. This field indicates the size of the segment in process memory. So it can be 0, but it is often larger than the file size. A common reason for that is that the segment might contain uninitialized data. In other words, data that doesn't have an initial value. This data normally gets initialized to 0 when it gets loaded into process memory. So space is needed for that data in the segment when it gets loaded into memory, but space is not needed for it in the file. So here we see in the field the value is 00000120. So that gives us a value of hex 0120, which is a decimal 288 bytes. So we note that this is 4 bytes more than the file size. The file size was 284 bytes. So this is likely due to there being 4 bytes of uninitialized data in this segment. In larger programs, you may see a much larger difference between the file size and the memory size. The memory size may be actually much larger than the file size due to a large amount of uninitialized data. So down here, I have an image of the segment to section mapping that we looked at earlier. So we're looking at segment 4 right now, and notice that one of the sections inside the segment is the BSS section. This stands for block starting symbol, or sometimes block started by symbol. And this is where uninitialized data is stored that is initialized to 0 when the program begins to run. Okay, so the next field we're going to look at is P flags. So P flags is a value of bitmask flags that are relevant to the segment somehow. So one thing that this tells us is the read, write, and execute permissions for this segment. So those are indicated by the first 3 bits of this 32-bit number. These are the low order bits. So we see here they define executable, writable, and readable. So what this is this is just a value of 1 shifted left by this many times. So in this case, it's shifted left 0 times, or 1 time, or 2 times. And so what this essentially does is this is bit 0, this is bit 1, and this is bit 2. And so if there's a 1 in that bit place, that indicates that this permission is set. So you'll notice here that in this particular elf file, we also have a couple other masks defined. And so this first one uses the high 4 bits right here for a processor specific flag. So in this case, it would be ARM. And then the next 8 bits are used for OS specific flags. So you may not see this in all elf files, and it may vary from processor to processor and from OS to OS. Another thing to note is that not all of the bits in this flag are used. So we've got, the low 3 bits right here, and then you got these 4 plus these 8. So that's 12 high bits and 3 low bits for a total of 15 bits that are used in this flag. So there's 17 bits in the middle that are not used, at least as they're defined in this elf file. So it's possible those could be used from some other purpose. So if you're doing debugging or reverse engineering, just pay attention to that. That could be important. All right, so if we look over here, we have the value for P flags. So this is, remember this is little Indian, so we have a value of hex 6. And hex 6 is in binary 110. And so we see here that the 0 bit is not set, but the 1 bit and the 2 bit are both set. Okay, so that indicates that it does not have execute permissions, but it does have read and write. Okay, so this corresponds to execute, this is write, and this is read. So here we say executable is not set, but write and read are set. Okay, so the next field we're going to go over, and the last field we're going to go over, is the P align. So the P align is the value that segments are aligned in memory and in the file. And so the elf.h has this wording right here. Loadable process segments must have congruent values for p v-adder and p offset modulo the page size. So remember, v-adder is the virtual address. So this is the address that it expects to get loaded to in memory. And offset is the location in the file itself. Okay, so for those of you that don't know, modulo is an operation, and basically what it means is it's what remains after division operation. So for example, if I take 5 divided by 2, then we would have a remainder of 1 because 2 goes into 5 2 times, but there's 1 left over. So if you do 5 modulo 2, you would have a result would be 1. So the way to explain this is a little confusing, and I think a lot of people mess this up. So for me, the easiest way to explain it is mathematically. And so what it's saying is that the virtual address modulo the align value must equal the offset modulo the align value. So that's what this wording right here says. So it's a little confusing, but that is what it means. Another thing to add is if this field has a 0 or a 1, that means no alignment is necessary. Okay. For load segments, though, you will normally see this type of thing right here. So if we come over here and we look at the value right here, so we have a value of 0, 1, 0, 0, 0, 0. So we bring that down here, and so we have this value right here. So that is our align value. So again, we bring this equation down here, and we have the virtual address modulo the p-align must equal the offset modulo the p-align. So here we have the virtual address, which we covered previously, is 20 Fox 0 Charlie. So that is where it expects to get loaded in memory. And we do a modulo operation with this value right here. It must equal Fox 0 Charlie, which is the offset in the file, must be equal to that modulo, this number right here. And so if we do the operation, we will see that we divide this by this, and the remainder is 0 Fox 0 Charlie. And if we divide this by this, the remainder is 0 Fox 0 Charlie. So this is good. Okay. So if we had another value, like let's say the virtual address was like 21 Fox 0 Charlie, then that would come out to be 1 Fox 0 Charlie, which would not be congruent, and so this wouldn't work. And so one reason that the OS might use this is if it uses the address space layout randomization, in which case the OS is going to decide where it loads. So it may not be this address that it's requesting, but it has to honor this alignment in order for it to work. Okay, so that completes the discussion of the program header structure. For those of you that are still with me, I commend you for your endurance, but there are a few more things that I'd like to point out about some segments. All right, so first I want to talk about the segment, the interp segment. Okay, so the interp segment is the interpreter segment, and this segment simply points to a null terminated string that contains the name of the linker or loader that the program is looking for. So in this case, we see here that it's the interpreter in the file is at file offset 154. Okay, and so if we go to that in the hex code, we can see here that we have some string data. These are ASCII. This is ASCII codes for strings, and so it corresponds to this /lib/ld Linux SO number 3. So LD Linux is a Linux dynamic linker loader, and it's responsible for preparing the program to run, finding shared libraries that the program needs, mapping them into memory, and then running the program. This linker loader, by this exact name, needs to exist on the target system in order for the program to run. This generally only exists when the binary is dynamically linked, and so if you have a binary that's completely statically linked, then you likely will not have this right here. So the next thing I'd like to point out is that segments can overlap each other. So you'll see here that the first load segment gets a load address, a virtual address of 10000, and has a size of 4 DC. Okay, so it spans from 10000 to 104 DC. So if we look at these other segments, we note that these right here, these segments right here, are inside that range. So all three of these segments right here are actually also inside this segment right here. Okay, but these segments themselves, they don't get loaded themselves, they just get loaded as part of this segment right here. You also notice that this one right here, this 10168, is also in that range. So this segment and these three right here are in this segment right here. And so you'll see this commonly, and that's okay. And also notice that here we've got this segment right here, which is 20 Fox 0 Charlie. And so if you look at that, you'll notice that this dynamic segment right here is inside that. And so these are generally used to help get the program running, but these two load segments are the only thing that actually get loaded into process memory. Okay, that brings us to the end of the video. So in this video, we talked about the structure of the ELF program header. We examined each field of the program header inside a binary file, and we looked at the structures and definition of the elf.h, the program header output from the readelf, and we examined the program header from a compiled binary looking at a specific segment as an example. So I hope you found this video useful. Let me know if you got any questions or comments. See you in the next video.